Welcome back. We are going to continue our discussion talking about the electron volt or EV. Okay, this is something that we measure on the microscopic scale, and it's the energy unit given to a fundamental charge accelerated through a potential difference of 1 volt. Okay, um, so we defined this as 1 eV is equal to 1.60 times 10 to the negative 19th coulombs, okay, times 1 volt. And then with some, excuse me, with some quick algebra looking at the units, there we go, there's the word, we find that 1 eV is equal to 1.60 times 10 to the negative 19th joules, okay? So an electron accelerated through a potential difference of 1 volt is given an energy of 1 electron volt, okay? So talking about energy brings up some memories of conservation of energy. Okay, so this is something that we would have discussed in the first part of Physics 2A. Okay, and this doesn't change no matter what we are looking at. So just a reminder, the total energy of a system is conserved if no net addition or subtraction of work or heat transfer is introduced, okay? And we know that electrostatic force is a conserved force, so it will follow this same conservation, okay? Reminder that mechanical energy is the sum of kinetic energy and potential energy of a system. Excuse me. So we get these ideas here. We have the addition of potential and kinetic energy is equal to a constant, or we can say this here, we have the initial kinetic energy plus the initial potential energy is equal to the final of the sum of the final. Okay, so we're going to use this idea to find out some interesting things of systems. So let's get started with example 19.3. We want to calculate the final speed of a free electron accelerated from rest through a potential difference of 100 volts. Okay, so our final speed would be like V sub F, just like with looking at gravity. Okay, when we were looking at gravitational forces, we did this a lot, or Newtonian physics. Okay, we're looking at kinematics. That's the word I was looking for. Okay, it's going to be very similar. So we have our final velocity and we have our potential difference here. Okay, so as I stated, we have a, I should say KE initial plus a potential energy initial equal to a kinetic energy final. I don't know why I keep changing the way I'm writing things, plus potential energy that is final. So let's go ahead and write this out. So our kinetic energy, remember, is 1/2 mv squared. This is initial. Okay. Our potential energy, that is something that we found back here. Okay. This is going to be our potential energy, or we can say it in this form here. So potential energy is, I can go ahead and write it. Potential energy is equal to Q times V. Okay, we're going to use that. And go back. So Q times V. Okay. And that's equal to our final kinetic energy should be 1/2. Oops, that should be an M. M V final squared plus Q V final. That should be initial. Okay. So note that we have our potential difference. We don't have initial or a final potential. So we have a potential difference, or delta V. Delta V is, of course, V final minus V initial. Okay, that's how we defined differences or changes in anything. Okay. Also note that in this problem it says that the electron was accelerated from rest. So this means our initial velocity is 0. Okay. Oops, initial. Okay. So this will cross out automatically because that goes to 0. So this whole term will be 0. We want to combine this guy and this guy. Okay, and we are looking for that final velocity here. So let's go ahead and fix this up. Let me go ahead and make these a little bit larger so you can tell the difference. I just noticed that that looks a little bit confusing. So it's going to be like bolded, okay? All right, so we've got Q, and if I bring this guy over there, we'll have VF minus V initial. Let's make it bold so that we know its potential energy. It's equal to, move that over there, is going to be negative 1/2 mVF squared. Okay, so we have Q delta V and 1/2 mVF squared. Oops. Okay. Now we have our potential difference here. I will need to look up the mass of an electron, and we know the charge. We just used that in the last video. But let's go ahead and solve for V sub F. So V sub F is going to equal negative 2 times Q, which is the charge, delta V, potential difference, divided by our mass, square rooted. Okay, so let me go ahead and get that. Okay, so our mass is 9.11 times 10 to the negative 31 kilograms, and our Q is 1.6 negative times 10 to the negative 19th joules. Okay. All right, so let's go ahead and start plugging stuff in. We have negative 2 times Q, negative 1.6 times 10, negative 19th joules, times delta V, which is 100 volts, divided by our mass of 9.11 times 10 to negative 31st kilograms, and all of that in a square root. Okay, so let me go ahead and start that. So 2 times 1.6 10 to the negative 19th times 100, divide that by 9.11 times 10 to the negative 31st. Okay, and then take the square root, and we get, wrong pen, whoops, 5.9, let's see how many units, 3 times 10 to the 6th, and this is going to be in meters per second, okay? I don't have all of these conversions here. Let's see, volts. What was volts again? So I have it here. joule per coulomb. Oops, sorry, too far. I'm just put note. Volt equals joule per coulomb. Okay, so that crosses out with that. No, it doesn't. Joule squared. What is coulomb? Okay, I'm not going to go through this real quick, but we know that these are all standard units. Working with all standard units, and it'll check out, okay? I'm not going to go through all the details. I know that joules has some sort of kilograms, meters, and seconds in it, and it will come to meters per second after taking the square root, okay? So this is our velocity, or speed, of a free electron that's accelerated from rest through a potential difference of 100 volts, okay? All right, let's move on to voltage and electric fields, okay? A lot of times we want to know the voltage between 2 points, A and B, and in terms of an electric field, okay? So with that, voltage between 2 points, A and B, is equal to the electric field E, okay, this is equal to E, times the distance between those 2 points. So this is for a uniform electric field, okay? And the distance would be between, for example, 2 plates. Okay, so we've got a plate that has all positive charges, a plate that has all negative. They're separated by some distance, d. Okay, we have some sort of electric field flowing between the 2 plates, and we can find that electric field is the voltage, okay, or that potential difference, delta V, is equal to, that voltage divided by that distance, okay? This image also says the work done, describes the work done, so this is work done, or just the work, is equal to the charge Q, whatever that charge is, times that potential difference at voltage, okay? Oops. All right, so let's go ahead and do a quick example of this. This is 19.5, states an electron gun has parallel plates separated by 4 centimeters and gives electrons 25 kilo electron volts of energy. So this is my potential energy here, and this is my distance d. Okay, what is the electric field strength between the plates? So again, we have some sort of plates here with some distance separating them, some flow of electrons. Okay. All right. Gives electrons 25. That is actually the voltage, I believe. Give me 1 second. Okay. So we have our voltage here between 2 points. So part A, we have electric field is equal to V AB divided by D. Okay, or we can say delta V, our potential difference, divided by that distance. Okay. I mislabeled this guy up here. That is our voltage. Okay, so this tells us we have 25 kilovolts. So using that information, we can find our electric field strength. which is going to be 25.0 kilovolt, divided by our distance, which this is the same as 0.04 meters. So we've got 0.04 meters. And what is that come out with? So 25 divided by 0.4, we have 625, and this is in kilovolt per meter. We can switch that over to volt per meter by saying for 1 kilovolt, we have 1,000 volts. Do we want to do that, or do we want to keep it here? Yeah, we can do that. So times 1,000, we get 6.25 times 10 to the 5th, and that is in volts per meter. So this is the electric field. Okay. So now we can move on to part B, which states what force would this exert on a piece of plastic with a, with this is the charge, 0.5 mu coulombs, that gets between the plates. Okay, so force is equal to Q times E. Okay, so this is our charge, so this is Q. Unplug that in as 0.500 mu times C. I'm sorry, mu coulombs. And then microcoulombs times our electric field, which is 6.25 times 10 to the 5th volt per meter. Okay. We will need to input what this mu is. That is 10 times 10 to the negative 6. Okay, so let's go ahead and do that. We take our 6.25 times 10 to the 5th, multiply it by 0.5 times 10 to the negative 6. Pen again. And we get a force of 125 times 10 to the negative 1. Actually, let me put this in simpler terms. 0.3113, and this is coulomb volt per meter. Okay, and we can again bypass the information or the nitty-gritty of making sure that this is a Newton. Okay, but this is 0.313 newtons. That is our force. Okay. All right. So we just found our electric field between two plates, and given that we put some sort of plastic or something in between that has a charge between those, what kind of force that would exert on that object. Okay. All right. Let me quickly mention this. This is voltage and electric field. So this is a way to look at the distance over which a potential takes place. So like from A to B, let's see, example from A to B. And then of course, delta V is the potential difference. And the division between the two, so electric field is equal to negative delta V over delta S. This minus sign shows that the electric field points in the direction of decreasing potential. Okay, so wherever we have a decrease in potential is where the electric field will point. Okay, and it's said to be the gradient of the electric potential. Okay, so this is what I'll leave you with. And again, if you have questions about anything, please let me know. And I will start on the next video with an example. All right.